Consider a particle undergoing uniform circular motion with radius r0. Its position is given by r equals r0 cosine omega t plus sine omega t, where omega is the angular velocity. Compute the velocity and the acceleration, and which way do the velocity and acceleration point relative to the position vector r(t). So, we have r of t equals r0, which is the radius of the circle, times cosine omega t in the I hat direction plus sine omega t in the j hat direction. And omega is the angular velocity. So to find the velocity, you simply take the derivative of the position. So dr of t over dt, sorry, you take the derivative with respect to time. That is equal to r0 times cosine, sorry, not cosine, r0 times negative sine omega t times omega plus cosine omega t times omega. And so, as you can see, we can actually take out an omega here. So this would be the velocity, which is equal to omega r0 times negative sine omega t in the I hat direction plus cosine omega t in the j hat direction. And now, to find the acceleration, you simply take the derivative of the velocity with respect to time. So dv over dt is equal to omega r0 times negative cosine omega t times omega plus negative sine omega t times omega. Let me write that neater. There we go. And so, as you can see, we can factor out another omega. So the acceleration becomes, and we can actually factor out a negative one as well. So negative omega squared r0 times cosine omega t plus sine omega t. And does this look familiar? Well, this is exactly what r of t is. As you can see, r0 times cosine omega t plus sine omega t. r0 times cosine omega t plus sine omega t. So a of t is actually negative omega squared r of t, or omega squared r, negative omega squared r. So that's part A. So now, what do the acceleration and velocity vectors look like when compared to the position vector? So if we have a circle, and this is radius r, or I suppose this is the position vector r, the velocity vector would be tangential to the circle. And it makes sense, because if you take the derivative of r at this point, you would get a vector that's tangent, but let me prove it to you another way. So, as you know, since these vectors are perpendicular to each other, if we take the dot product of them, it should equal 0. So, let me do r cross v. So, r cross v. And that would equal to, sorry, r dot v. R dot v. And that would equal to, so r dot v is equal to this quantity right here. And so let's actually take the dot product. So the way you take the dot product of two vectors is you simply multiply the components together. And since the components are multiplied together, when the i's multiply, it simply equals 1. And when the j's multiply, that also equals 1, since it's a unit vector. And so this quantity should equal 0. So from here, we would just factor out, yeah, you would factor out an omega r naught squared. And that would be cosine omega t times negative sine omega t plus sine omega t cosine omega t. And as you can see, this plus this is equal to 0. And so r dot v is equal to 0. And that's why the velocity vector is tangential or perpendicular to the position vector. And now we by looking at the equation for the acceleration, we can see that it's a negative times a constant times the position vector. So from that we just know that the acceleration is going to be pointing this way into the circle. And if you've done circular motion before, you know that this makes sense, since that's how the object travels. That's how the moon travels in circular motion with respect to the Earth.